Okay, so today we are going to be going into rules of inference and the other stuff. So before we go into that, just to remind you that we are talking about validity, and validity is just an argument is valid if and only if the premises are true, then the conclusion must be true. That's all that deductive validity is. And so like we covered the semantics and the syntax of prop logic, right? And the definition I gave with respect to um, with respect to like validity being like if all the if the so we can go by like a semantic understanding. The semantic understanding would be if all the premises have true in the truth table, then the conclusion must also have true for the argument to be valid. Like every single time where all the premises are true, the conclusion needs to be true. That's sort of like a semantic understanding of validity, right? From there, we can go into other stuff which are related. Like for example, we are interested in making valid inferences, and we are also interested in showing that certain inferences are deductively valid and other inferences are deductively invalid, right? So that's where the concept of proof comes in. So I'll just introduce the concept of proof. um, I'll just use proof. Okay, so roughly speaking, what's a proof? A proof is simply a sequence of well-formed formulas, um, such that every single premise follows from previous well-formed formulas, and well, every single one, as in um, apart from the original premises, every single line will follow from the previous premises, such that eventually we reach the conclusion. Okay, so think of a proof like um, let me just change color. So a proof will be basically you have some original premises, right? P1, P2. Let's say these are the two premises. So there's something written here, something written here. And then what you'll do is we can start from, so we also have the conclusion. So this is the argument. So this is basically the argument. Uh, okay. And then what we are trying is going from these premises to the conclusion, and we are trying to show how that is happening. So we have P1, P2, these are the original premises, but then we add like additional premises which will show which will basically take from P1 and P2 and eventually show that it is reaching. So like for example, let's say it takes you like 5 steps. So you do 5 steps, and the fifth step will be basically identical to C, and it will basically be the same as the conclusion. So essentially you're showing that the truth of P1 and P2 leads to the truth of the conclusion using certain rules, and that set of rules is what we call rules of inference. um, are you following that much?
So far, I think so. I'm not too sure where P3 and P4 are coming from, but
Yeah, so
maybe
P1 and P2, right? There could be some P1 and P2, and P3 and P4 are just sort of like restating P1 or P2, or they are like applying, or P3 and P4 are derived by applying certain rules of inference on P1 and P2. Okay, so such that eventually you get P. So this is sort of like a rough way to put it. Maybe showing you a proof will be more helpful. So but yeah, I think we can do that later. So for now, we can just say that so a proof or a proof is also called a derivation, but like a proof is just a sequence, or a sequence of WFFs such that every WFF is a premise, or it like is an assumed premise, or it follows from previous premises. Yeah, is a premise, sorry, an assumed premise follows earlier WFFs. Okay, so that's sort of like the definition of a proof. Yeah, and this is done so like follows from earlier well-formed formulas using certain rules, and that's the rules of inference. Or it could be either. It could be a rule of inference, or it could also be a rule of replacement. Okay, so that's sort of like the definition of a proof. We'll try to make it make more sense when we try to do a proof. So until then, I'll just remove this part. Okay. What are the rules of inference? Basically, rules of inference are kinds of like, there are certain inferences, in the sense that they are certain argument forms which are valid according to the syntax and semantics of propositional logic. So for example, you could also think of them as you know or let me show you an example. So this is like, it's sort of like a story. Okay, so the story goes, so there was a guy called Achilles, and he had like a tortoise. Okay, and he tells the tortoise that um, like, hey, you could, well, he says that you know I can give like an argument, like they have some debate, and then he is like, okay, I can give you the argument like this. Okay, so this is the argument that the guy gives to the tortoise, and the tortoise is like, what if I accept this, and I do accept this, but I don't accept this? Okay, so then the guy was like, okay, I will give an argument for that. I'll be like, P implies Q, and P entail Q, P implies Q and P, therefore Q. Okay, so the tortoise says, okay, I'll accept this, but I'll not accept this. The conclusion basically. So the guy is like, okay, then I'll give you an argument which is P implies Q and P and sorry, one sec. P implies Q and P imply, oh sorry, fucking up the brackets. Yeah, so I'll just add another bracket. And the entire thing P implies Q and P implies Q, and this whole thing basically implies Q, so that therefore Q. Okay. So I think you're seeing the obvious problem here. The problem here is that it started with this argument, but then it sort of went into an infinite regress, right? Like you started with P implies Q, P therefore Q, and you just like we can just infinitely go in, like we can just keep expanding this over and over again. However, if you just have this as a valid inference according to the prop logic, if you just sort of make it a rule, then every instance of this kind of inference structure will always be valid. So on this system, this will always be true. So this is always a valid argument. Are you following that much?
I didn't really understand what you did here. Yeah.
Okay, yeah. So basically, what I'm trying to do is I'm trying to show you that there is, like, if you just don't have certain, like, if you don't have rules, right? Then you can sort of always accept the premises, but reject the conclusion. But if you if you have the rules, like if you just formally introduce this inference, you know, this inference, if you just introduce that as a rule in the system, then you have no scope of accepting both premises but rejecting the conclusion. Like if you accept both premises, you must accept the conclusion. So these kinds of rules are what we call rules of inferences. So they are basically always valid regardless of what. So like for example, yeah, basically like a rule, I'll just introduce rules of inferences and then list out all the rules. Okay, so rules of inferences are just you know, like how we had in syntax, they are rules that govern valid inference. Okay, so these rules govern valid inference. So basically the idea is, if you have some argument, it will be like if you have a valid argument, you can prove that this argument is valid if you apply these rules of inference to it. You know, that's kind of the idea. So we can, I guess we can start listing out each one of the rules of inference, and like if you want, we can draw an accompanying you know, sort of truth table to show that. One sec.
Would be good. Yeah.
Yeah. Okay, yeah. So basically there are certain rules which have been specified, and in these are like these are like set of rules which have already been sort of formalized inside prop logic, and they are like just like each one of them is sort of like a tautology, because they are true in all cases. um, but yeah, so we can go through each of the rules. So the rules of inference, I can also add that these are all like valid inference forms. So if you have an argument, if you just make your argument follow certain patterns like these, the argument will always be valid. That's sort of the um, yeah, yeah. So yeah, I guess we can start listing out each of the rules. Which one we sure? Yeah, I guess we'll start with modus ponens. This is the granddaddy of all inferences. It's probably the most used inference rule by me personally. I'm not sure about others, um, but most of my arguments follow this kind of a. So what is modus ponens? Okay, modus ponens, the general form, uh, is this. Okay, general form. Alpha implies beta. Remember, alpha and beta are meta-linguistic variables, so you can basically replace alpha and beta with any proposition, any well-formed formula, and you will get modus ponens basically. So you have alpha implies beta, P2 alpha, and the conclusion will be therefore beta. This is a valid argument, and it's called modus ponens. Any argument, any well-formed formula that replaces these, if you see this pattern, it's always a modus ponens. Now let's draw a truth table that is showing this. So we have alpha and beta. You know how to draw a truth table. It's just true, true, false, false. And this one is true, false, true, false. Okay, and then you have you start having the premises. So you have the first premise, which is alpha implies beta. And then you have the second premise, which is alpha. And then you have the conclusion. Sorry, one sec. Beta. Okay, so this obviously, it's true, false, true, true, and this is the same as this. So true, false, false, and this is also the same as this. So true, false, true, false. Now find me all the instances where all the premises are true.
So in the first row.
That's right. Yeah, this one, right? So this is where all the premises are true, and lo and behold, the conclusion is also true. Is there any other case where it is where all the premises are true?
No.
Okay. So wherever you find all the premises to be true, you also find the conclusion to be true, which is why this is a valid argument. So whenever you use a modus ponens, it will always be a valid argument. Okay, so I've sort of shown you, like even just semantically, that this is, um, this is a valid argument, right? And you can replace alpha and beta with anything. You can replace this with like, it can be P and R imply Z, P and R, therefore Z. This is also a modus ponens. Basically, you can replace alpha with any well-formed formula. Okay. Uh, okay, so that's the first one. So I guess we can go to the second one. The second one will be modus tollens. It's called modus tollens. Okay. And the general form will be P1, P2, conclusion. P1 will be alpha implies beta. It is the same as the first one, except in this one you have not beta and the conclusion is not alpha. Okay, so this is also a valid form and I'll show it to you with the truth table. I'll just copy paste this truth table. Okay, this much. So the premises will be not beta, so that will be F T F T. Okay, I'm just applying the negation rule here. Then we have not alpha, and that will just be F T T. Now tell me which rows have all trues, all true premises.
The last row.
The last row, yeah, this one. And wherever you have all trues, you also have the true conclusion. So this is also a valid argument. Okay, all of these are going to be valid because that's what the rules of inference are. So by definition they're going to be valid. Then we can move to the third one. Let's do disjunctive syllogism. Okay, you need to remember these names, by the way.
How many are there?
I think there are like 10 or 12. Let me count. So we have modus ponens, modus tollens, disjunctive syllogism, hypothetical syllogism, constructive dilemma, and then wait, what are the other ones? Conjunction, addition, simplification. Yeah, those. So that's like how many? 1, 2, 3, 4. Yeah, you could say around almost 10. Like, we will count them towards the end. Don't need to worry about it. But yeah, so this is like disjunctive syllogism. again the general form will be P1, P2, and conclusion. So we have alpha or beta. Let's say not alpha, therefore beta. Okay, this is disjunctive syllogism. It's called disjunctive syllogism because it uses there's a disjunction here, right? So there's a disjunction here, and it's a syllogism. Syllogism is just like another word for argument. Okay. Yeah. So let's draw the truth tables. I could just copy paste it. And I'll just change this. Can you tell me what's the truth table for disjunction?
So false.
False.
Oh, we're doing inclusive disjunction, right?
Yeah.
Okay, so true.
Mm-hmm.
True. True. False.
Okay. Yeah. So that's the first premise. Then the second premise is not alpha. And then the conclusion is gonna be beta. Okay. What's the truth table for not alpha?
So false, false, true, true.
Okay. And beta?
That's what we have in column number 2.
Yep. Okay, find me all the rows with true premises.
Now it's row 3.
Row 3, yeah. Both of them are true. What do you see? The conclusion is also true. So that's another valid argument. So that's number 3. Number 4 is called hypothetical syllogism. The general form of this is again P1, P2, conclusion. Alpha implies beta. Beta implies gamma. Therefore, alpha implies gamma. Okay. So this is what we call a hypothetical syllogism. It's a bit like, how in maths you have the property of transitivity. If A equal to B and B equal to C, therefore A equal to C. So that's roughly the same thing that's happening over here. I'll draw the truth table and I'll tell you some quirks about this. So we have the same truth table. Just a sec. Alpha implies beta, beta implies gamma. So for that you'll need another column, right?
We have 3 variables here.
Yeah, exactly. So we'll need to reconstruct this. We'll have to expand the table.
we're going to need an extra rows as well.
Yeah, of course. So alpha, beta, gamma. Tell me how to draw this.
So we got, in this one it's 2 to the power of 3, so using our rule 2 to the power of n, we have 4 truths and then 4 falses, if I remember correctly.
Yes.
And after that, once you draw the last f, we take the 8 and we divide it by 2, so we get 4, and then the 4 just tells us how many truths we get before we change to falses. So it's 4 t's and then 2 t's, sorry. So you divide by 2, yeah.
Yeah, so you have true, true, false, false, true, true, false, false. And then you have
You
t.
take the 4 divided by, yeah. So just to be clear, the first row you take the 8, you divide it by 2, so you get 4, and then the second row you take the 4 divided by 2,
Yes.
you get 2, and then the third row.
You take the 2 and you divide it by 2, so you get 1. So yeah. So we are going to have to expand this as well. What would this be?
1 minute. So we have a false going to true, so this is true.
Okay.
True. True, true.
Okay. Hey, that's wrong. We have to redraw the column. Do it again.
Okay, so true. True. False. False. True. True. True, true.
Yes, that's more like it. Then here,
Here, true. False. True. 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 False. True. True.
okay. Let's do this.
So true. False. True. False. True. 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 True.
Yeah. Find me all the columns with truths.
So the columns where we have
Sorry,
the premises
yeah.
as true and the conclusion also as true. So
No. Just
the
find
first-
me the columns and rows where find me the rows where the premises are true. We'll forget about the conclusion for now. Just find all the
Okay,
premises
so
to be true.
the
Yeah.
first row,
Okay, this one.
and then we also have was it number 5?
Yeah, this one.
And then the last 2,
Yeah.
7 and 8.
Yeah. So again, if you find the premises are true, the conclusion is also true. Here the premises are true, the conclusion is also true. Here also the premise is true. Here also the premise is true, and the
So
conclusion
it's
is
a
true.
valid argument.
Exactly. So this is also a valid argument. So this is a hypothetical syllogism. Now, okay, we can do one of two things. We can discuss the rest 4 argument forms and do some proofs, or do you want to, or what do you want to do? Do you want to do some proofs right now using these four?
So, will we cover all of the 10 or 11 you said today?
I mean, we can, but it's up to you. Like, we can do one of two things. We can either cover all the rules today and do all the proofs in the next session, or we can do proofs using the rules that we have learned up till now.
Let's do the second one. So just using the proofs, using the rules up to now.
Okay, yeah, that's fine. Okay, we can do that. All right, so let's do some proofs. This is the fun part.
Looking forward to this.
Okay. So I'll just move over here so that we don't interrupt the list, right? Like, because if I do it there, we'll have to come back to the list. So I'll do the proofs over here on the side. Okay. So let's doing some practice proofs. We are doing some practice proof. Practice proof. Okay. So I'll give you an argument. Again, this is from the book. Let me just check the book 1 second. So V implies W implies X. Okay. V implies okay, this is premise 1. Premise 2 is V. Premise 3 is not X. And the conclusion is not W. So our job is to prove that this is a valid argument. So how would you approach it? There are, again, we have two ways to do it, right? One is of course the one is of course the truth table. Yeah. And the other is doing a natural deduction. So do you want to do the truth table first and then do the natural deduction?
Well, I don't know what a natural deduction is. Have we done that yet? I don't think so, right?
No, but we will be doing it. That's in the I mean we can, so let's do it with the truth table first and then we'll do the natural deduction. Okay,
Cool. So then we have to write down the number of variables we have
yep,
in the truth table. So here we have V, W, X. That's it.
okay, and
I guess we can copy the truth table we had at the bottom.
Yep. Okay, I got the table. What's the first premise? V
1 minute. Yeah.
implies W implies X. Okay. So for this, you will need to draw W implies X, right? Because
Yeah, we should do a column for that first.
yeah, exactly. Because it's a compound proposition. And then we have let me just demarcate that this is, and we have V implies W implies X, so that'll be another column. So the next one will be the next premise, which is v. We can just copy paste the entire thing. Then we have not x, and we have not w, right? Okay, let's fill this. So that's true.
P, yeah. And then false, true, 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 false, true, true.
Okay. So
And I
here
guess
you'll have to, yeah.
you can put some brackets, I guess, around
Sure.
the W and the X, right?
Yes, you're right. You're right.
And then, yeah, so we have true, false, true, 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 true.
Okay, great. And this I'll just okay. Next one.
So then we just take the X column and we make yeah, negative.
And this one is just gonna be F F D.
TT. TT.
Okay, find me all the true premises. So this is P1, this is P2, this is P3.
So we have row number 4.
Row number 4. Okay, then that's all.
That's all, I believe. Yeah.
Yep. Okay, what's the conclusion?
Also true.
So this
So
is
it's
also
valid.
a valid argument. Okay. So this is of course the truth table way of proving validity. So let's do the natural deduction. Okay. And we'll end the session with this particular example. We'll do more next time. So the step 1 of doing validity is to just write all the premises again. Okay. V implies x. I'll draw brackets. P2 is v, P3 is not x, P4. Okay, so I've written all the 3 premises, right? The 4th one is a conclusion, so I'm not writing that right now. But look at this. What does that look like to you?
It looks like modus ponens? Or?
Modus ponens, exactly. So P4, you can just write W implies X. And how did you get that? You got it by applying. So what you do is you write that, you apply modus ponens to this, and then you write P1, comma, P2, you put a hyphen, and then you write modus ponens, abbreviated as MP. Okay. Now, what does this look like?
One minute, let me have a look at. Could you show me hypothetical syllogism again? So I didn't write that one down actually.
I don't think you need hypothetical syllogism.
Then it looks like it could be modus tollens.
Exactly. Yeah, it's a modus tollens. Yeah. So basically, you have a conditional. The consequent is negated, and that's basically modus tollens. Okay. So what will be the modus tollens of this? So if you apply modus,
Before we do that, it was yeah, for P4 so when you wrote like W implies X, so you always take what's, so you took the consequent.
consequent, yeah.
So in this case now we're looking at P3, right? As the P3 is the
Negation of the
it's-
consequent.
so it's the second premise of modus tollens, right?
Yeah.
So then P5, what do? We take the consequent of P4, or
One.
what do we do?
So what's modus tollens?
So modus tollens is alpha implies beta.
Okay, we have alpha here, we have beta here. So that's alpha goes beta. Then what's the second premise?
Not beta.
Not beta. So we have not beta here. Right? Look. So this is alpha. This is
Yeah.
beta. What is this?
So that's okay, not beta.
Yeah. So the order doesn't matter. You can.
Okay.
Yeah. It doesn't
So,
have to
yes,
be
yeah.
the first premise is the conditional, the second premise is the negated consequent. It doesn't have to be like that. It could be anything.
All right, I see. Because I was thinking the first premise of modus tollens is alpha goes to beta.
Yeah, the order doesn't matter. Okay. So, what would P5 be based on these two?
Do we take the consequence of P of, or do we just take the consequent of P4?
What's the conclusion of modus tollens?
Conclusion is not alpha.
Okay, what's alpha in this case?
W.
Yeah, so the conclusion is not W. You got that? Do you want me to go through the entire proof once again?
1 minute, I just need to, I guess we could do it one more time.
Okay, yeah, that's
I
fine.
just, so I'll need to just read it a little bit in my spare time as well.
Yeah,
So
yeah.
I
No,
don't
no,
think
no, it's
my
fine.
brain is fast enough to capture all of that.
No, 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 it's fine. Yeah, you're tracking, don't worry. So what's the first premise? So the first three premises will be the same as the main argument, right? So we are just writing V implies W implies X. Okay? So these are the three premises. Now, what you can do is just look at, you don't need to do this, but just think of this as alpha, think of this as beta, and think of this as gamma. Okay, you don't need to do this, just like for the sake of explaining, I'm trying to do this. Okay, and this entire thing you can think of as delta. Okay, so alpha implies delta, alpha, therefore delta. That's what you get in modus ponens. So like I'll just remove this. Okay, so what does this argument form look like to you?
So, as we said, it looks like modus ponens.
It looks like a modus ponens. So I'll write
So what are we trying to do with P4 exactly? Like, if you had to say in one sentence, what are we doing exactly? Yeah.
So what we are doing is we are deriving a formula from existing formulas by applying the rules. So we are trying to do a proof, right? So
Yeah.
I'm deriving P4 from the existing premises by applying some rule of inference. Okay?
Okay, so because normally the conclusion, it comes after P3.
Yeah.
So when we add P4 and P5, does the conclusion also come after P5 at the end?
No. Don't forget about the conclusion for now. Now we are just focusing on the premises.
Okay.
Okay? Yeah, just keep the conclusion in the back of your mind. Not W is the conclusion, just keep that in the back of your mind. But for now, just focus on this. Okay? This is V. Okay? Then you have W implies X. That's the consequent of V.
Yeah.
And in modus ponens, when you affirm the antecedent, you the inference is the consequent.
Yeah.
So what's the new premise now here?
I see. So then we just write W to implies X.
Exactly. And this we have derived from the previous premises.
Okay. Yeah, I see what you did there.
Yeah, exactly. And to explain how I got this, I will just write P1 and P2. I applied modus ponens.
Okay.
Okay?
Yes, so far I'm following that.
Okay. Now, look at these two. Look at P3 and P4. What kind of argument form do they look like?
So it looks like a form of, as we said, modus tollens.
Modus tollens. And what's the conclusion supposed to be here? What can you derive from these two?
Okay, so normally it's not alpha from modus tollens. So in this case, then not alpha it's going to be not W, right?
Not W, exactly. So you have a conditional, you have negated the consequent here, and you basically the inference is that you get the negation of the antecedent.
No, you're back. You cut off for a second.
Oh, okay, sorry, yeah. So
Yeah.
I was saying, so you have the conditional, and modus tollens is when you have a conditional and the negated consequent. So you have the negated consequent, and the conclusion of modus tollens is the negated antecedent. So in this case, the negated antecedent is not W.
So
Okay.
yeah, the extra premises what we're adding, it's the conclusions of the rules that we've seen.
Yes, exactly. So these are steps, like how in maths you have some equation and then you have steps and then you get to the final equation that you want to get to. So P3 and P4 and P5 are like steps. Okay. So how did we get this?
Using modus tollens, so then there'll be P4 comma P5, I'm guessing. Then
No.
a dash.
Not P4 comma P5. On which premises?
P3 P4. Yeah.
Yes, P3 P4. P3 P4 modus tollens. Okay. And you got not W. Now check the conclusion of the main argument.
Same.
It's the same, exactly. So you have arrived at the conclusion, therefore not W. And that's hence proved. So when you finish a proof, you write QED. It's Latin for quod erat demonstratum.
And what does that mean?
It just means that we have shown it. Like, hence we have shown it.
Okay. So yeah, I think it's clearer to me what the proof is doing. So we're just trying to use the rules to get the rules to get the conclusions from the rules, and then seeing if by adding these conclusions to our current argument, we get the same conclusion as from
Yes. So this is the proof. So this section is the proof. What you're doing is
yeah.
you are taking the premises. These are the premises. Okay. Okay. I think I'll write it in a different color so that it's more obvious. So these are the premises, right? From the premises, you derived additional formulas, right? From the premises, you applied certain rules of inference, and you obtained new well-formed formulas. And it turned out when you applied the rules of inference to these new well-formed formulas, you got the conclusion. So that's what a
that.
proof is.
Yeah, I think that's okay for me.
Yeah. So
Makes
basically
sense.
that's an example of a proof.
Okay. Yeah, at the start I wasn't too sure what a proof was, but
Yeah.
I guess.
Yeah, that's why. So when I just say this, right, when I just tell you that a proof is a sequence of well-formed formulas such that it's either an at least is a sequence of well-formed formulas such that it is an assumed premise, or it follows from an earlier well-formed formulas using the rule of it doesn't make sense. But if I show you this, okay, so this is a sequence of well-formed formulas that follow that follow from earlier premises. So this is like two well-formed formulas which follow from earlier well-formed formulas by applying some rules of inference, and from there you eventually get the conclusion. So this process is called proving the argument's validity in this case.
So sort of proving that the conclusion is there from the original argument, right?
Yeah, you're proving that given the premises, if the premises are true, the conclusion logically follows from those premises. That's what
Great.
you're proving.
Yeah.
Yeah.
It's okay for me.
Yeah. And once you do this, you write quadrat demonstratum, and that's like the biggest joy of a logician is to write hence proved. But yeah, this is an example of a proof. Next time, I guess we'll do some more proofs. And next time we will not use the truth table because it takes hell of a lot of time to draw each of the columns and stuff like that. So we'll not do that. We'll just do the, so this is called this entire thing is called a natural deduction.
Okay.
Okay. That's
one of the one of the the ways you said last time.
Yeah.
You said there were truth tables and a natural deduction.
Yes. So this is a natural deduction.
Okay, and will truth tables have any more utility going forward?
I don't think so. I mean, we probably will be getting back to them now and then. Probably we will do it. Yeah. We will get back to it when we are doing rules of equivalence. Because I want to show that this is equivalent to this, and I can do that using a truth table. But yeah, until we get to rules of equivalence, we are not gonna be doing any more truth tables.
Okay. I think rules of equivalence is after this. It's
Yeah,
the next
after
one.
this, yeah. So we have four over here, then we have addition, then we have constructive dilemma, we have simplification, and one more, I think. Let me check. Oh yeah, conjunction. So you have conjunction, addition, simplification, and constructive dilemma. Those are the four rules of inference that we are left with. Um, yeah, those are all the rules of inference. So there's 8 rules of inference.
Right, so those will be for next time.
Yeah, the rest 4 will be for the next time, and then after that we have the rules of equivalence. There are, I think, 10 rules of equivalence.
So rules of equivalence or rules of replacement,
Yeah,
they're the same thing.
yeah. So that's
Okay.
1, 2, 3, 4, 5, and 1, 2, 3, 4, 5 rules of equivalence. So that's yeah, 10. So 8 rules of inference and 10 rules of equivalence, or rules of replacement. So you in total you have 18 rules. Apart from, of course, you have the rules of well-formed formulas, constructing well-formed formulas themselves. So yeah, those also will be added. So that's like 20 something rules.
That's a lot.
Yeah, I mean, so like after a point, it sort of becomes second nature. Um, like I whenever I look at this, right? Whenever I look at, oh sorry, where is that? Yeah. Um, oh man, we've covered a lot. Yeah. Whenever I look at this, I immediately see a modus tollens. I immediately see a modus ponens. Um, and whenever I see an opportunity, I just apply the rule. So that's how. So it's kind of like second nature to me right now. So you'll get there. So once you have like enough practice, you'll also see this, and instantly you will derive this. You'll see this and instantly derive this, and then like it'll be very, yeah, it'll be very good.
Come like instinctively.
Yeah.
Okay.
Yeah. So I guess that should be enough for the day.
I think so too.
Yeah. So I'll end the recording then.
Great.